A star dies in a silent, brilliant flash, but its story is just beginning. A strange and persistent glow lingers in the void long after the fireball fades. This is not just a dying ember, it is a radioactive signature, a cosmic fingerprint left by the most violent alchemy in the universe. Today, we are learning to read that light. The mysterious glow from events called macronovae is more than a spectacle. It is a new form of cosmic technology. By the end of this exploration, you will understand how this radioactive decay glow could unlock the secrets of deep space travel and reshape humanity's future among the stars. What forged the gold in your jewelry, and could the same power fuel our ships to other solar systems? The answers lie in a beautiful, deadly light that has been shining in the darkness for eons, waiting for us to understand its message. What do you believe we might find when we finally learn to speak the language of starlight? This cosmic fingerprint is written in the aftermath of a specific, spectacular event, a collision of unimaginable density. To understand the glow, we must first meet its source, the macronova. Also called a kilonova, this explosion is the cosmic middleweight champion. It is not the cataclysmic end of a giant star, which we call a supernova. That is the heavyweight, a titan's final roar. A macronova is different. It is the violent, beautiful merger of two neutron stars. These are the leftover cores of dead stars, crushed by gravity into spheres so dense that a single teaspoonful would weigh as much as a mountain. Picture two such objects, each a city-sized ball of pure nuclear matter, locked in a final, fatal dance. They spiral inward over millennia, and then, in a fraction of a second, they smash together. The collision is so violent it shakes the very fabric of space-time, sending out ripples we call gravitational waves, but the true magic happens in the debris. The impact blasts a colossal cloud of stellar material into the void, a cloud superheated to billions of degrees and laced with the raw ingredients of atoms. In this cosmic forge, neutrons are captured at a staggering rate, building elements atom by atom in a process called rapid neutron capture. This is where the universe forges its heaviest treasures. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that can power a city, all of it is cooked in these fleeting, brilliant explosions. The macronova is a jeweler and a physicist, a destroyer and a creator all at once. Its initial flash is blinding, but as that fireball expands and cools, a new light takes over, a glow with a story to tell. What happens when that radiant cloud, filled with freshly minted, unstable atoms, begins to settle? This second, lingering light is the true mystery. As the blinding flash of the merger fades into the expanding cloud of cosmic debris, a new kind of luminescence takes hold. It is a soft, persistent glow that can shine for weeks, sometimes months, long after any conventional heat from the initial explosion should have dissipated into the blackness of space. So what is powering this marathon of light? The answer is not simple thermal radiation. It is something far more fascinating and fundamental. This sustained luminosity comes from the very atoms themselves, trembling apart from the inside. It is the glow of radioactive decay. In the chaotic forge of the collision, countless unstable, heavy elements were created. Think of elements like platinum, gold, and uranium, but in forms that are fresh, hot, and profoundly unsettled. These newborn atoms are radioactive, meaning their nuclei are packed with an unstable excess of energy. To find stability, they must shed that energy particle by particle in a process that transforms them into different, quieter elements. Each tiny atomic breakdown releases a burst of energy, often as a high-energy photon of light. Multiply that process by 1 billion trillion unstable atoms in that vast cloud, and you get a collective, enduring shine. It is a glow born from elemental transformation. You can find a faint earthly echo of this in the eerie, greenish glow of old radium watch paint, where radioactive decay excites a phosphor. Or in the surreal blue Cherenkov radiation in a nuclear reactor's water pool, where particles move faster than light can travel in that medium. But here, in the aftermath of a star's death, the scale is almost incomprehensible. It is the universe's most magnificent nuclear battery, powering a beacon with the slow, inevitable unraveling of matter itself. This atomic unraveling is the engine of the glow, but what built these unstable atoms in the first place? The story begins with a process so violent and rare it only happens in the most extreme corners of the cosmos. It is called the rapid neutron capture process, or the R process for short. To understand it, think of building with atomic Legos under impossible pressure. Normally, when a star forges elements through fusion, it adds protons and neutrons together slowly, step by step, building from hydrogen up to iron. But the environment inside colliding neutron stars is not normal. It is a soup of unimaginable density, flooded with a torrent of free neutrons. Here, atomic nuclei do not have the luxury of time. They are bombarded, absolutely showered, with neutrons faster than they can even process them. Imagine trying to eat while someone is pouring an endless stream of popcorn into your mouth. You cannot chew or swallow, you can only capture. That is what happens to atomic nuclei. A seed nucleus, perhaps a bit of iron or nickel, is hit by a relentless wave of neutrons. It cannot decay or adjust. It can only frantically capture neutron after neutron after neutron, growing heavier and heavier at a breathtaking rate. This runaway assembly line creates forms of matter that are utterly alien and profoundly unstable. It builds isotopes, which are versions of elements with different numbers of neutrons that could never exist on Earth. We are talking about forms of californium, einsteinium, and elements far beyond uranium on the periodic table, substances with names and properties we are only beginning to theorize. These newborn isotopes are born hot, bloated, and deeply unhappy. They are overstuffed with neutrons, holding together through sheer force in an environment that has just vanished. The moment the merger cloud expands and that neutron flood stops, these super-heavy nuclei are left in a quiet void, utterly unstable. They have only one path forward: to decay. They must shed that excess energy and those extra neutrons, stepping down the ladder of stability through a series of radioactive decays, each step releasing a little burst of light or a particle. This cascading decay chain, from these exotic, short-lived giants down to stable elements like gold and platinum, is what powers the long, slow fade of the macronova's glow. It is a light born from the frantic construction and inevitable collapse of matter itself. This cascade of radioactive decay is not a single event but a breathtakingly complex chain reaction, a cosmic domino effect played out on an atomic scale. Each newly forged, unstable isotope does not simply vanish in a puff of light. Instead, it transforms, often into another element that is itself unstable, which then decays into something else, and so on, down a ladder of instability. This is a decay chain, a multi-step nuclear journey from frantic creation to final, quiet stability. Picture a row of dominoes, but each domino is a different size, shape, and color, representing a different atomic element. Knocking over the first one sets off a sequence where each falling piece triggers the next. In our expanding cloud of stellar debris, trillions upon trillions of these atomic domino chains are tumbling simultaneously. At every single step in this cascade, energy is released. Sometimes it is a burst of high-energy gamma-ray light, invisible to our eyes but carrying immense power. Other times, it is the ejection of a beta particle, a fast-moving electron, or an alpha particle, which is essentially a helium nucleus. Each of these emissions carries kinetic energy away from the decaying atom. And here is the crucial part: all that energy does not just disappear into the void. It gets absorbed by the surrounding material in the debris cloud. Think of it like this: if you had a vast, dark balloon filled with glitter and you set off thousands of tiny flashbulbs inside it, the entire balloon would light up from within. The decay energy acts like those internal flashbulbs. It heats the cloud from the inside out, keeping it hot and luminous long after the initial fireball of the collision has cooled. This internal heating is what sustains the macronova's glow across the entire electromagnetic spectrum, from X-rays down to visible light and into the infrared. It is not one color or one type of light. It is a full symphony of radiation, all powered by the relentless, step-by-step unraveling of matter. This internal atomic symphony paints the sky with a color-changing light show unlike any other. The glow from a macronova is not a single, static color. It evolves, telling a story of changing actors in its radioactive cast. In the first frantic days after the collision, the light can appear intensely blue, even violet. This is the signature of the fastest, most energetic decays, the initial shockwave of instability from those freshly forged, super-heavy elements. Their breakdown releases such a torrent of high-energy photons that the entire cloud radiates with a blistering, short wavelength blue. But as days turn into weeks, something remarkable happens. The fastest decays burn out quickly, like flashbulbs popping and fading. Their role in the light show ends. Now, slower decaying isotopes take center stage. These elements, like strontium or cesium, release their energy at a more measured pace, producing light skewed toward longer, redder wavelengths. The brilliant blue fades, washing out into a cooler crimson red, a visual confirmation that the decay chain is marching onward through time. Astronomers do not just watch this color shift, they dissect it with a tool called spectroscopy. By splitting the macronova's light into a rainbow spectrum, they can search for dark lines or bright bands at very specific colors. Each element in the periodic table absorbs or emits light at a unique set of wavelengths, a chemical fingerprint. In the light of several observed macronovae, scientists have detected the clear fingerprints of heavy, unstable elements like tellurium and cesium, substances that can only be created in abundance through the rapid neutron capture process. It is like finding a signed confession at the scene of a cosmic crime. That faint red glow is not just pretty, it is proof, direct observational evidence that the violent R process we theorized is actually happening out there, forging the universe's heaviest elements in real time. So when we look at that distant, fading crimson light, we are not just seeing a dying ember, we are reading a live inventory of a cosmic forge, a receipt for the creation of elements that may one day wind up in planets and perhaps in us. That crimson signature in the void is more than a scientific curiosity, it is a birth certificate. Every macronova event is a cosmic alchemist, a fleeting forge that seeds the galaxy with the very building blocks of complexity. In a single, violent eruption, a neutron star collision can forge hundreds of Earth masses worth of precious and heavy elements, then blast them across interstellar space at a fraction of light speed. This stellar shrapnel, rich with gold, platinum, uranium, and rare earths, eventually mixes with clouds of gas and dust. Over eons, those enriched clouds collapse to form new stars, and around those stars, new planets coalesce. The iron in our blood came from the death throes of massive stars in supernova, but the iodine in your thyroid, essential for life, the neodymium in the powerful magnets of your headphones, the platinum that cleans car exhaust, and yes, the gold in a wedding band or a microchip connector, these are gifts from a different kind of stellar death. They are the children of macronovae. Without these cataclysmic mergers, the periodic table would be barren beyond iron. There would be no heavy elements to form rocky planets like Earth, no radioactive elements in the core to keep our planet geologically active, no complex chemistry that could ever lead to life or technology. These events are the ultimate recyclers, taking the collapsed remnants of dead stars and transforming them into the seeds of future worlds. So when you hold a piece of jewelry, you are holding stardust, yes, but not just any stardust. You are holding a fossil from one of the universe's most violent and creative explosions, an event that made a complex technological universe possible. Our very existence is tied to these ancient, brilliant flashes in the dark. The faint crimson fingerprint of a macronova is an astronomer's holy grail, but catching one in the act requires a new kind of cosmic detective work. The hunt begins not with light, but with a ripple in the fabric of space itself. This is the domain of gravitational wave observatories like LIGO and Virgo. These are not telescopes in any traditional sense. They are the most sensitive rulers ever built. Picture 2 4-kilometer long arms arranged in an L shape, with lasers bouncing down their length in perfect vacuum tunnels. When a gravitational wave from a cataclysmic event, like 2 neutron stars spiraling together, passes through Earth, it minutely stretches and squeezes space itself. One arm gets imperceptibly longer while the other gets shorter, by a distance far smaller than the width of a proton. The lasers inside detect this microscopic wobble. So, while our eyes see nothing, these instruments hear the universe. They pick up the thump, the final chirp, of 2 unimaginably dense objects colliding billions of light years away. That chirp is an alert, a cosmic siren saying, "Look here now." But a gravitational wave signal alone is like hearing a distant crash in a pitch-black forest. You know something monumental happened, but you cannot see what it is or where the debris landed. To see the glow, you need eyes, and they need to move with incredible speed. The moment an alert is issued, an automated race against time begins. A network of rapid response telescopes, both on the ground and in orbit, swings into action. Satellites like the Neil Gehrels Swift Observatory, which sees in X-rays and ultraviolet, immediately pivot to the patch of sky identified by the gravitational wave signal. On Earth, powerful robotic optical telescopes from Chile to Hawaii to the Canary Islands autonomously point their giant mirrors, capturing the first flickers of the emerging glow. The Hubble Space Telescope and its successor, the James Webb Space Telescope, join the effort, peering deep into the infrared to see through any obscuring dust and analyze the chemical composition of the expanding cloud. This global collaboration, from feeling ripples to capturing photons, creates a multi-messenger portrait of a single event. But this is just the beginning of a new era of discovery. Soon, a revolutionary instrument will change the game entirely. The Vera-C Rubin Observatory, currently being built in Chile, will not wait for a gravitational wave alert. Its mission is to scan the entire visible sky every 3 nights with a camera the size of a small car. It will be an unstoppable surveyor, watching for any change, any new point of light that wasn't there before. It promises to find not just 1 or 2 macronovae a year, but potentially dozens, painting a statistical picture of how often the universe forges gold and how these events shape galactic evolution. We are moving from chasing rare cosmic sirens to taking a nightly census of stellar creation. The first true portrait of a macronova arrived on a date now etched in astronomical history, August 17, 2017. For the first time ever, gravitational wave observatories LIGO and Virgo felt the distinct rising chirp of 2 neutron stars spiraling together, a signal so strong and clear it set off a global frenzy. This was not another black hole merger which leaves no light to find. This was the signal everyone had been waiting for. Within hours, observatories across the planet and in space swiveled toward a patch of sky in the constellation Hydra. A prize was found almost immediately, a brilliant new point of light catalogued as GW170817, blazed in a galaxy 130 million light-years away. For days, it outshone its entire host galaxy. This was not a single observation, it was a symphony. Every instrument humanity could point at it joined in. Gamma-ray telescopes caught the initial fierce burst of energy. Optical and infrared telescopes watched hour by hour as the brilliant blue fireball expanded and cooled, its color shifting day by day toward a deep, predictable crimson. Radio telescopes tracked the expanding shockwave plowing into interstellar space. X-ray observatories monitored the aftermath, revealing the structure of powerful jets of material that had narrowly missed pointing directly at Earth. The data was a treasure trove that confirmed decades of theory in a single event. The light curve, the precise way the brightness faded over time, matched the predicted power source of radioactive decay perfectly. Spectroscopy of that reddening glow revealed the unmistakable fingerprints of heavy elements like strontium, proving the rapid neutron capture process was not just a neat idea on a chalkboard. It was real, and it was happening right in front of us. GW170817 became the Rosetta Stone of high-energy astrophysics, a single event that translated the language of gravitational waves into the language of light and chemistry. It showed us that the universe's forges are active, that our gold has a violent origin, and that we now possess the tools to watch it being made. That one event in August 2017 did more than confirm a theory. It ushered in a new way of seeing the cosmos entirely. We have moved beyond simply watching the sky. We are now learning to listen to it and even to feel its vibrations. This is the heart of multi-messenger astronomy, and macronovae are its perfect poster child. For centuries, astronomy was the study of light. Every discovery, from Galileo's moons to the expansion of the universe, came from analyzing photons, those tiny packets of electromagnetic radiation, whether they were visible light, radio waves, or X-rays. It was like trying to understand a symphony by watching the violinists through a soundproof window. You could see their fingers move, see the intensity on their faces, but you couldn't hear the music. Multi-messenger astronomy smashes that window open. It is the practice of observing a single cosmic event through multiple, fundamentally different channels of information, and then weaving those threads together into one coherent story. A macronova gives us not one, but three distinct messengers. First, we feel it. The gravitational waves are the initial tremor, the deep bass note of the collision itself, carrying details about the masses and spins of the neutron stars. Then we might catch a whisper. Neutrinos, those nearly massless ghost particles that fly through planets like they are not even there, could theoretically stream out from the ultra-dense core of the merger, though they are fiendishly hard to detect. Finally, and most gloriously, we see it. The entire electromagnetic cascade, from the initial gamma ray burst to the shifting optical glow to the lingering radio echo, paints the detailed aftermath. Each messenger carries a unique piece of the puzzle. Gravitational waves tell us about the dynamics of the crash. The light tells us about the chemistry and physics of the debris. By combining them, we move from a blurry snapshot to a high-definition movie with a soundtrack. It transforms astronomy from a visual art into a full sensory experience for science. We are no longer just astronomers, we are cosmic interpreters, learning the complete language of the universe. But that beautiful, creative light has a terrifying twin. The same cataclysm that forges gold can also unleash one of the most destructive forces in the universe. When two neutron stars collide, the unimaginable energy does not just explode outward in a sphere. Often it is channeled, focused into a pair of narrow, ultra-relativistic jets that scream out from the poles of the merger at over 99.9% the speed of light. These jets are the engines of short gamma-ray bursts, the most luminous electromagnetic events known to exist. For a few seconds, a single such jet can outshine every star in 100 billion galaxies combined, all concentrated into a beam of radiation no wider than a few degrees. It is a cosmic blowtorch of pure energy, and its direction is a matter of life and death on a planetary scale. If such a jet were to be pointed directly at Earth from somewhere within our own Milky Way galaxy, the consequences would be catastrophic. The initial blast of gamma rays and X-rays would not just light up our sky, it would violently ionize our upper atmosphere. This would trigger a chain of chemical reactions that would obliterate the planet's protective ozone layer. Within days, Earth's surface would be bathed in lethal levels of ultraviolet radiation from our own sun. The result would likely be a global mass extinction event, wiping out the base of the food chain and collapsing ecosystems. This is not science fiction, it is a sobering astrophysical possibility, a reminder that the universe is not only beautiful but also indifferent and profoundly dangerous. The odds of a nearby neutron star merger aiming its deadly beam directly at us are astronomically low, perhaps once in hundreds of millions of years. But for a species contemplating a future among the stars, understanding this risk is not optional, it is essential. This is where the radioactive decay glow becomes a crucial diagnostic tool. By carefully studying the light curve and the spectrum of a macronova, astronomers can piece together the geometry of the explosion. The glow tells a story about how much material was ejected in a spherical shell versus how much was funneled into those narrow jets. It helps answer critical questions. Did this particular merger produce a powerful, focused jet, or was its energy more evenly dispersed? Was the jet pointed directly at us, or were we seeing it from a safer, off-axis angle? Each macronova we observe adds a data point, helping us model the physics of these extreme events and statistically map the hazards of our galactic neighborhood. For a future civilization with colonies spread across multiple star systems, this knowledge is a fundamental part of risk assessment, a way to evaluate which regions of the galaxy might be safer for long-term settlement. The soft crimson glow, therefore, is more than a beacon of creation. It is also a warning light, helping us read the safety signs on the highway of the cosmos. That crimson warning light also holds a map to our future homes. Beyond assessing danger, the faint glow of distant macronovae is quietly sketching a new kind of chart, a chemical map of the cosmos. Each event is a data point, a single measurement in a vast galactic survey. By simply counting how often these mergers happen in different galaxies and carefully analyzing the unique elemental signature of each one's glow, astronomers are beginning to trace the story of how galaxies grow up. They are writing a chemical history of the universe. Think of it like this. Imagine you are an archaeologist trying to understand the history of a great civilization, but you cannot visit its cities. Instead, you study the trash heaps it left behind, the composition of the garbage, the types of pottery, the metals used in tools, all tell you when different technologies were developed and how wealth was distributed. A macronova is the universe's trash heap, but also its mint, the specific blend of heavy elements we see in its light, the ratio of gold to platinum to rare earths, tells us about the conditions inside that particular cosmic collision. But more importantly, by looking at many such events across different types of galaxies, we can see a pattern emerge. Young, primitive galaxies formed early in cosmic history should have very few heavy elements. The stars within them have not had time to live, die, and enrich the galactic environment through supernova and mergers. In these galaxies, a macronova's glow would tell a simple story, dominated by the very first waves of element creation. But in older, mature galaxies like our own Milky Way, the story is more complex. The gas and dust between stars is already polluted, as astronomers charmingly call it, with the ashes of countless generations of dead stars. A neutron star merger happening today in such an environment uses this pre-enriched material as its starting point, so the resulting glow carries a more complicated signature, a layered history. By building up a census of these events, we can literally watch a galaxy become chemically mature. We can see the concentration of precious and heavy metals rise over cosmic time. This is not just abstract history, it is a practical guidebook for future exploration. If we want to find star systems with the best chances of hosting rocky, Earth-like planets, we should look for regions with a rich chemical heritage. The elements forged in macronovae and supernova are the very ingredients for terrestrial worlds. A star born in a metal-poor neighborhood is less likely to form a robust system of rocky planets. But a star formed in a region mapped as chemically rich by the glow of past mergers, that star has a much higher probability of spinning a family of solid, complex worlds. So this soft radioactive light does more than tell us about the past. It highlights the targets for our future. It points the way to the galactic neighborhoods where life, and perhaps a new home for humanity, is most likely to have taken root. That crimson light is a cosmic power meter, and its reading is almost beyond comprehension. The soft, lingering glow we see from a distant macronova represents just a whisper, a tiny fraction of the total energy released in the collision. The vast majority of the power is carried away invisibly in gravitational waves and neutrinos, or blasted into narrow jets of gamma rays. Yet even this leftover sliver, this radioactive afterglow, can briefly outshine every single star in its host galaxy. The numbers are staggering. In its peak, a macronova's glow can release more energy in a single second than our Sun will produce over its entire 10 billion-year lifetime. We are talking about energies measured in octillions of megatons, figures so large they lose all meaning to the human mind. This forces a profound question. For a civilization that dreams of spanning stars, could such power ever be harnessed? This is the realm of speculative yet grounded futurism. On the theoretical scale used to measure a civilization's technological advancement, known as the Kardashev scale, humanity is not even a Type 1. We are a Type 0, still drawing all our energy from the plants, fossils, and minerals of our home planet. A Type 1 civilization would harness all the energy falling on its planet from its star. A Type 2 civilization, a truly stellar culture, would capture the entire energy output of its star, perhaps by building a vast structure like a Dyson sphere. But the energy from a stellar merger is of a different category entirely. It is a brief, titanic spike that dwarfs the steady burn of a star. For a hypothetical Type 2+ civilization, the notion of mining such an event is a staggering engineering puzzle. It is not about building a sphere, but perhaps about predicting these mergers with pinpoint accuracy millennia in advance, and then deploying some form of unimaginable energy-absorbing infrastructure at the precise location in interstellar space. One might picture a swarm of billions of self-replicating probes, lying in wait for centuries, ready to unfold into a net of energy collectors at the moment of collision, capturing the radiative glow and the particle streams, converting a cosmic catastrophe into a once-in-an-eon power boost for an entire interstellar society. While this remains firmly in the realm of science fiction today, the exercise is not pointless. It serves as the ultimate calibration for our imagination. Contemplating such a feat forces us to truly internalize the awesome power scales that govern the universe. It is a reminder that the phenomena we observe as beautiful, distant lights are in fact the engines of cosmic change, operating at levels of energy that redefine what is possible. Our journey from reading that faint red glow to ever dreaming of touching its power is a journey that spans the entire history and future of intelligence itself. The same physics that lights up a distant galaxy could one day propel our ships between the stars. While harnessing a full macronova remains a fantasy for the distant future, the radioactive isotopes forged within them represent a tangible, albeit incredibly challenging, technological possibility. Consider the sheer energy density locked inside these unstable atoms. On Earth, we use nuclear fission in power plants, splitting heavy atoms like uranium-235 to release energy. But the exotic isotopes created in a neutron star merger, substances like californium-252, operate on a different level entirely. Their decay is so rapid and energetic that a single gram of californium-252 releases over 200 million neutron emissions every second. It is a microscopic powerhouse. The energy density of these macronova-born materials is millions of times greater than chemical rocket fuel, and even surpasses conventional nuclear fission fuels by orders of magnitude. For a spacecraft, this is the ultimate dream fuel, a substance where an incredibly small mass could provide an enormous amount of thrust for a very long time. The concept is known as nuclear radioisotope propulsion. Instead of a traditional reactor with controlled chain reactions, the spacecraft's engine would use the natural, relentless heat from the decay of these isotopes. That heat could be used to supercharge a propellant like liquid hydrogen, expelling it at tremendous speeds to generate thrust. Or, in a more advanced design, the emitted particles themselves could be channeled and focused by magnetic fields to create a direct thrust. A ship powered by such an engine would not need the colossal fuel tanks of chemical rockets. It could accelerate steadily for years, building up to a significant fraction of light speed, making journeys to nearby star systems conceivable within a human lifetime. This is the principle behind theoretical generation ships or fast interstellar probes. The power source would be compact, long-lasting, and unimaginably potent, a direct echo of the processes that keep a macronova glowing for months. Of course, the obstacles are monumental. These isotopes are fantastically rare on Earth, often produced only in minute quantities in specialized particle accelerators for research or medical use. They are also intensely radioactive, requiring shielding and handling technologies we can barely conceive of. The idea of harvesting them from actual cosmic debris is, for now, a pipe dream, a task of interstellar mining on an impossible scale. Yet the principle stands as a North Star for advanced propulsion. It tells us that the universe itself has already invented the ultimate engine fuel in the hearts of colliding stars. Our challenge is to learn to replicate, or perhaps someday to responsibly use, a fragment of that stellar alchemy. To journey to another sun, we may first need to master the power of a star's death. The power to travel between stars is not the only gift these cosmic forges offer us. Beyond physics and engineering, the light of a macronova touches something deeper within the human spirit, reshaping our art, our philosophy, and our very sense of place in the universe. When the first true color image of a kilonova's afterglow was translated from raw data, it was not just a scientific document, it became a source of awe. That luminous cloud of crimson and gold, a cosmic watercolor painted by radioactive decay, has since appeared in digital art, inspired symphonic movements, and fueled the pages of new science fiction. Artists are no longer limited to imagining stellar cataclysms. They can now collaborate with astrophysicists to visualize real events, using real spectral data to choose their palettes. The result is a new genre of cosmic realism where the beauty is not invented but revealed. This fusion of data and creativity does more than produce stunning visuals, it acts as a bridge. It translates the abstract mathematics of neutron capture and decay curves into an emotional experience anyone can feel. A listener might not grasp the intricacies of the R process, but they can be moved by a musical piece that sonifies the changing light curve, translating a month-long fade from blue to red into a haunting, descending melody. This is how profound science enters the culture, not through textbooks but through shared wonder. This artistic impulse springs from a philosophical realization that is now grounded in hard evidence. The phrase "we are stardust" is often used poetically, but Macronovae research has turned it into a precise chemical truth. We are not just generically made of star stuff, we are, in part, the literal debris of the most violent explosions in the cosmos. The iodine in your body, the gold in a circuit board, the uranium that can power a city, these atoms were forged in a cataclysm that briefly outshone galaxies. This knowledge fosters a radical sense of connection. You are not a passive observer looking out at a distant, foreign universe. You are the universe looking back at itself. Your very existence is a continuation of a chain reaction that began with the collision of dead stars billions of years ago. This cosmic perspective can dissolve feelings of isolation and insignificance, replacing them with a profound belonging to an ancient, dynamic, and creative cosmos. In a future where humanity lives among the stars, this perspective will inevitably shape daily life. Imagine the architecture of a habitat orbiting a quiet star. It might not be sterile and metallic, but designed to reflect our cosmic heritage. Walls could be inlaid with alloys whose composition mirrors the elemental signature of a famous kilonova, a constant, tangible reminder of our origins. Public spaces might feature dynamic light installations that slowly shift from blue to red over the course of a month, mimicking the light curve of a stellar merger, turning astrophysics into ambient experience. Even personal mindfulness or meditation practices could evolve. Instead of focusing solely on the breath, one might contemplate the journey of a single atom of gold, from its frantic birth in a neutron flood to its long, cold voyage across interstellar space until it finally found a home in the ring on someone's finger or the circuitry of a starship's computer. This is more than trivia. It is a foundational narrative, a story that ties our past to our future. It suggests that a society living in space will not define itself by the technology that keeps it alive, but by the depth of its connection to the cosmos that created it. The ultimate lifestyle impact of understanding macronovae may be this: a future where we don't just live in space, but where we feel consciously, meaningfully at home there, because we finally know where our home truly came from. This profound connection to the cosmos is no longer a spectator sport. The hunt for the faint radioactive glow of distant cataclysms has opened its doors, inviting anyone with curiosity and an internet connection to become a cosmic detective. This is the world of citizen science, and it is transforming how we explore the universe. While giant telescopes and gravitational wave detectors capture the raw data, the sheer volume of information is staggering. Computers are excellent at processing numbers, but the human eye and brain remain unmatched at recognizing subtle patterns, odd shapes, and anomalies that might signal a new, fading light in the heavens. This is where you come in. Online platforms like the Zooniverse host projects where volunteers from around the world can log in and examine real astronomical images. You might be presented with a sequence of pictures of the same patch of sky, taken days or weeks apart. Your task is simple: look for a new point of light that appears and then fades, the telltale signature of a transient event like a macronova or supernova. By classifying these images, you are directly contributing to the discovery pipeline, helping professional astronomers sift through mountains of data to find the needles in the cosmic haystack. Your living room becomes a frontier outpost for discovery. Beyond analyzing images, you can now receive cosmic alerts on your phone. Applications and services linked to observatories can send you a notification the moment a new gravitational wave candidate is detected or a potential kilonova is spotted. These alerts often include coordinates, inviting you to step outside and look toward that patch of sky, knowing that a billion-year-old story of creation and destruction is unfolding in that very direction, even if your eyes cannot see it. This is not just about crowdsourcing labor, it is about building a global community of observers, a network of human consciousness all focused on the same point in the cosmos. It represents a fundamental shift in our relationship with the universe. We are moving from a model where a small priesthood of scientists interprets the cosmos for everyone else, to a participatory culture where millions feel a direct sense of ownership over our collective exploration. In a futuristic, engaged society, this connection is vital. It means that the wonders of multi-messenger astronomy are not locked away in journals, but are part of the public conversation, inspiring the next generation of engineers, artists, and explorers. When a major discovery is announced, it is not just a triumph for a distant research team. It is a victory for the retired teacher in Madrid, the student in Mumbai, and the farmer in Iowa who all helped scan the data. This democratization of discovery ensures that as we reach for the stars, we bring all of humanity with us, eyes wide open, searching for the next faint glow in the dark. That same cloud of newly forged elements, the beautiful source of the crimson glow, carries a hidden and deadly legacy. It is a wave of galactic radioactive fallout spreading silently through the interstellar medium at a significant fraction of light speed. For any vessel traversing the cosmic ocean, this presents a unique and invisible hazard. Picture a starship on a centuries-long journey to a promising exoplanet. Its course, plotted using the best maps from centuries before, takes it through a region of space that appears perfectly empty and serene. Unbeknownst to the crew or the ship's autonomous systems, that region was crossed by the expanding debris shell of a macronova just a few decades prior. The cloud itself is incredibly diffuse by human standards, more vacuum than substance, but it is permeated by high-energy particles and intense gamma radiation streaming from the decaying atoms within. Flying through it would be like sailing a wooden ship through a ghostly, invisible cloud of acid and fire. The ship's hull might be physically unscathed, but the radiation dosage for anything biological inside, or even for sensitive electronics, could be catastrophic. Acute radiation sickness would be a swift and grim certainty for an unshielded crew, while prolonged exposure could fry a ship's computer cores and navigation systems, leaving a ghost ship adrift. This transforms the beautiful afterglow from a mere scientific signal into a critical navigational warning. Future interstellar charts, the maps used by generation ships or fast automated probes, will need to be dynamic and constantly updated. They will look less like static road maps and more like live weather forecasts for the galaxy. Just as ancient mariners marked reefs and storm regions on their parchment maps, and just as modern pilots consult real-time turbulence and volcanic ash reports, starfarers will need to consult galactic hazard databases. These would chart the estimated expansion fronts of known macronova remnants, modeling their propagation over centuries. The faint, fading glow we detect from Earth today is not just a historical record. It is a beacon marking the current location of an advancing wave front of radioactivity. A navigational computer would plot a course that gives these glow zones a wide berth, adding years or even decades to a journey to ensure safety. This adds a profound new layer to the challenge of exploration. The universe is not just vast and empty, it is also periodically and unpredictably polluted by these events. Finding a clear path to another star will require more than a powerful engine. It will demand an exquisite understanding of cosmic history and a map that remembers every brilliant, dangerous flash that has ever occurred in our galactic neighborhood. Mapping these radioactive frontiers requires a tool far more powerful than any telescope, a digital universe built inside the world's most advanced supercomputers. To understand the chaos of a neutron star collision, physicists cannot simply watch the light. They must recreate the entire cataclysm from first principles, atom by atom, in a virtual space. These are not simple animations, they are full-scale numerical relativity simulations, some of the most computationally demanding tasks ever attempted. They must solve Einstein's equations for warped space-time, model the complex fluid dynamics of nuclear matter, and track the nuclear reactions of billions of particles all simultaneously. A single simulation can consume millions of processor hours on machines like the Oak Ridge Leadership Computing Facility's Frontier supercomputer, generating petabytes of data that represent a fraction of a second of real cosmic time. The output is a breathtakingly detailed digital replay showing how the two ultra-dense stars spiral, distort, merge, and erupt. From this virtual debris cloud, researchers can then simulate the rapid neutron capture process, watching as a torrent of digital neutrons floods virtual atomic nuclei, building up those unstable, heavy isotopes. Finally, they calculate how those isotopes would decay and what kind of collective glow that decay would produce across the electromagnetic spectrum. This digital glow is then meticulously compared to the actual light curves and spectra captured by our telescopes. It is a constant cycle of prediction, observation, and refinement, where the supercomputer's virtual reality helps us interpret the universe's actual reality. But what if you could step inside that simulation? The next frontier is not just observing the data, but experiencing it. Imagine a classroom of the near future where students don virtual reality headsets. With a gesture, they zoom into the heart of a supercomputer's simulation, not as a flat-screen graphic, but as an immersive, three-dimensional environment. They stand in the void as two neutron stars, rendered as swirling, crystalline structures of unimaginable density, spiral toward each other in silent, graceful slow motion. The collision unfolds around them, a shockwave of energy and matter expanding in a sphere. Then the view shifts to the atomic scale. The students watch as a sea of neutrons, visualized as a shimmering silver mist, bombard seed nuclei. They see those nuclei swell, capturing neutron after neutron, transforming into larger, unstable elements that pulse with a dangerous inner light. Reaching out a virtual hand, they could pluck a freshly forged, unstable isotope of gold from the chaos, watching as it trembles and decays in their palm, shedding particles and shifting down the periodic table toward stability, each step releasing a tiny burst of light that contributes to the surrounding crimson haze. This is more than a spectacular demo, it is a profound shift in scientific intuition. Complex three-dimensional relationships, the shear density gradients, the chaotic pathways of the R process, all become intuitively graspable in a way graphs and equations can never achieve. For the next generation of astrophysicists and engineers, this immersive tool could train their instincts, helping them see the universe not as a collection of abstract numbers, but as a dynamic, physical system they can literally navigate. The supercomputer provides the truth of the physics, and virtual reality provides the pathway for human minds to truly inhabit it, turning the most violent event in the cosmos into a comprehensible and even beautiful story. The digital universe can reconstruct cataclysms, but our own planet may hold physical evidence of real ones. We are searching for the ancient scars of nearby macronovae right here on Earth, buried in the deepest layers of our world. This is not astronomy with telescopes, but geology with a cosmic twist, a detective story written in atoms. The premise is both simple and profound. If a neutron-star merger happened close enough to our solar system, within perhaps a few hundred light-years, its expanding shell of radioactive debris would have eventually washed over us. This would not be a wave of visible light, but a silent rain of exotic particles and rare isotopes, settling onto the planet's surface and mixing into its geological record. Finding that signal today means looking for a needle in a haystack the size of the planet, an isotopic anomaly that defies all earthly explanation. Researchers are turning to some of Earth's most pristine natural archives to find it. They examine layers of ferromanganese crusts which grow on the deep ocean floor at a rate of mere millimeters per million years. These crusts slowly accumulate metals from seawater, acting as a continuous, ultra-slow-motion recorder of the ocean's chemical composition over tens of millions of years. Within those dark metallic layers, scientists search for minute traces of plutonium-244. This is a radioactive isotope with a half-life of around 80 million years, too short to have survived from the formation of Earth, but long enough to potentially linger if it fell from the sky relatively recently in geological terms. Finding a spike of extraterrestrial plutonium-244 in a specific layer would be like finding a distinct layer of ash from a particular volcano, a time-stamped marker of a cosmic event. Other teams drill into ancient Antarctic ice cores looking for traces of iron-60, another radioactive isotope produced in supernova and possibly in neutron star mergers. This iron-60 is not from Earth. It is interstellar dust, and a concentrated layer of it in the ice could signal when our solar system passed through a cloud enriched by a nearby stellar explosion. The ultimate pristine record, however, may lie not on Earth but on the Moon. The lunar surface, untouched by water, wind, or plate tectonics, is a perfect museum of cosmic bombardment. Lunar soil, or regolith, has been accumulating layers of interstellar material for billions of years. A sample core drilled deep into the Moon's surface could contain a clean, uninterrupted history of our galactic neighborhood's violent events, including the precise isotopic fingerprints of ancient Macronovae. Finding such evidence would change our understanding of Earth's history. It would tell us that our planet and our ancestors have literally weathered the fallout from a stellar collision. It would provide a concrete date for when such an event happened, allowing us to look in the fossil record and ask a haunting question. Did a wave of cosmic radiation, subtle but persistent, influence the course of life on our planet? Could it have triggered mutations, spurred extinctions, or perhaps even created evolutionary pressures that steered life in new directions? The search turns our planet into a crime scene, and geologists into forensic investigators looking for the atomic residue of a billion-year-old stellar murder. The radioactive atoms forged in those ancient cataclysms carry within them a perfect, unyielding rhythm. This is the heartbeat of the cosmos itself, a pulse so reliable we can use it to tell time across billions of years. It is a field called cosmochronometry, and it turns the universe's own debris into its most precise clock. The principle is beautiful in its simplicity. Every radioactive isotope decays at a fixed, immutable rate. We call this its half-life, the time it takes for half of any sample of that material to transform into something else. It is a statistical certainty, a ticking that cannot be sped up or slowed down by heat, pressure, or the passage of eons. On Earth, we use this for carbon-14 dating, measuring the decay of that isotope in ancient organic material to determine its age. But for the universe, we need a clock that ticks much, much slower. We need an isotope with a half-life measured in billions of years, one that was present at the very dawn of our galaxy. The perfect candidate is uranium-238 with a half-life of about 4.5 billion years, roughly the age of our solar system. But to use it as a clock, we need to find it in the right place, a stellar time capsule. Astronomers search for the most ancient stars in the Milky Way, small, dim stars known as metal-poor halo stars. These are the galactic elders, formed from the primordial gas clouds that existed soon after the galaxy itself coalesced. They contain only the elements forged in the very first generations of stars, the ashes of the earliest supernova, and critically, the very first macronovae. When we point our spectroscopes at one of these ancient suns, we are not just analyzing its light, we are taking a blood sample from the infant Milky Way. By measuring the precise ratio of uranium-238 to a stable element it decays into, like lead, or to another radioactive isotope with a different half-life, like thorium-232, we can perform a simple calculation. It is like finding an hourglass buried in the sand. We can see how much sand has fallen from the top chamber into the bottom. Since we know exactly how fast the sand falls, we can calculate precisely how long ago the hourglass was turned over. In the star, the turning over was the moment it formed, locking within it the radioactive elements from the macronova that seeded its birth cloud. The math gives us a number, a date. The oldest stars dated this way tell us the Milky Way is approximately 13.6 billion years old, forming not long after the Big Bang itself. That faint, long-extinguished glow from the first neutron star mergers did more than create gold. It wound the clock that now allows us to read our galaxy's birthday. We are using the nuclear ashes of the universe's first great acts of creation to write our own cosmic history book. That cosmic hourglass, wound by ancient mergers, also holds the key to a mystery of unimaginable density. To truly understand the glow, we must peer into the heart of the neutron stars themselves, into a realm where matter ceases to behave in any way we recognize. The brilliant afterglow is our only flashlight into this absolute darkness. When two neutron stars collide, they do not simply bounce off each other like billiard balls. They tear each other apart, and in that moment of destruction, they spill their guts. The cloud of debris and, crucially, the specific cocktail of heavy elements we see glowing within it is a direct sample of their internal material. Think of it as a cosmic biopsy. The light signature tells us what was ejected, but to understand why that particular mix of elements was ejected, we must ask what it was like inside the star before the collision. This is where physics reaches its limits. A neutron star's interior is a place of such extreme pressure that atoms are crushed out of existence. Electrons are forced into atomic nuclei, merging with protons to form a sea of neutrons packed together with almost no empty space. This is often called neutron soup, but that is a deceptively simple term. Under such conditions, this soup may undergo bizarre phase transitions, becoming a superfluid that flows without friction, or a superconductor that carries current without resistance. Some theories suggest the core may contain exotic particles like hyperions or even free quarks, breaking down the neutrons themselves into their fundamental constituents. It is matter in a state that simply cannot exist anywhere else in the observable universe, not even in the largest particle colliders on Earth. Our models for this matter are equations on a page, educated guesses about physics under conditions we can never replicate. But the macronova's glow provides a critical test. The violence of the merger and how much material gets flung out depends intimately on the stiffness or softness of this neutron star matter. If the interior is very stiff, resisting compression, the colliding stars might bounce apart more dramatically, ejecting a larger amount of material. A larger, richer cloud of debris could mean a brighter, longer-lasting radioactive glow and a different blend of heavy elements. If the interior is softer, more of the stars might plunge directly into a black hole, leaving less debris to glow. By carefully measuring the brightness, duration, and color of each macronova we observe, we are essentially taking the temperature of neutron star matter. Each event is a data point that helps physicists refine their equations of state, the mathematical descriptions that predict how this extreme matter behaves. A single glow in the distant sky is therefore a laboratory report from a universe-sized experiment, one testing the laws of physics under the most severe conditions nature can devise. It is how we study the impossible, by reading the light from its aftermath. The equations of state we refine today will be tested by a new generation of eyes, instruments so powerful they will turn our current glimpses into high-definition movies. The future of observing these cosmic forges is not just about bigger mirrors on the ground, but about placing our most sensitive detectors in the silence of space itself. Leading this charge is a mission that will listen to the universe in a whole new way, the Laser Interferometer Space Antenna, or LISA. This is not a telescope, but a gravitational wave observatory of staggering ambition. Picture 3 spacecraft flying in a perfect triangular formation millions of kilometers apart, with lasers linking them in a celestial web. In the pristine quiet of their orbit, free from Earth's seismic rumble, they will be exquisitely sensitive to low-frequency gravitational waves that ground-based detectors like LIGO cannot hear. This is the key. While LIGO hears the final, frantic chirp of neutron stars in the last seconds before collision, LISA will hear their entire courtship. It will detect the gravitational hum of these dense objects spiraling together for months, even years, before they finally merge. This gives astronomers something priceless, a prediction. LISA will not just tell us where a merger happened, it will tell us where it is going to happen, sending an alert that could give telescopes across the solar system weeks or months to prepare. to stare at a single point in space and capture the very first photon of the cataclysm. It will extend our hearing to mergers from the earliest epochs of the universe, revealing how often these events shaped young galaxies. To complement this cosmic hearing aid, we will need eyes with unprecedented vision. Envision massive space telescopes, successors to James Webb, designed not as general-purpose observatories but as dedicated hunters of transient cosmic fire. Their primary instrument would be an ultra-sensitive, rapid-response spectrograph, a device that can split light into its constituent colors with phenomenal speed and precision. From the moment a LISA alert comes in, this telescope would lock onto the target and begin taking a spectral reading not once a day, but every hour, every minute. It would watch in real time as the first unstable isotopes begin their decay chains, capturing the exact moment a specific element's fingerprint appears and then fades as it transforms into the next link in the nuclear ladder. This would not be like reading a finished book. It would be like watching the ink dry on each individual letter as the story is written. We could trace the nuclear reaction pathways directly, moving from theoretical models to a direct observational ledger of cosmic alchemy. But to truly understand the engine of the glow, we need to sense a messenger that has so far eluded us from these events: neutrinos. These ghostly particles stream directly from the heart of the ultra-dense merger remnant, carrying untouched information about the temperatures and processes at the core of the explosion. Catching them is the ultimate challenge. Future missions might involve placing vast neutrino detectors in deep space, using the moon itself as a shield and a platform. A detector on the far side of the moon, protected from Earth's radio noise and cosmic ray interference, could act as a pristine net, waiting to catch a handful of these elusive particles from a nearby merger. A confirmed neutrino signal, timed precisely with the gravitational wave chirp and the first light, would be the trifecta. It would pinpoint the exact moment of collapse, tell us what the core was made of, and directly measure the energy powering the radioactive furnace. This multi-messenger future, with LISA whispering the prophecy, giant eyes capturing the light show in exquisite chemical detail, and neutrino hunters feeling the core's pulse, will transform a faint crimson glow into a complete biographical portrait of matter's most extreme transformations. Mastering the universe's most violent alchemy forces us to confront a profound responsibility. We are learning to read the language of stellar death, and one day we may attempt to speak it. The power to create or manipulate the very elements forged in Macronovae, to harness that radioactive decay for our own ends, is not just a technological frontier, it is an ethical one. This is playing with cosmic fire on a scale we can barely comprehend. If a future civilization could synthesize californium or other super-heavy isotopes in vast quantities for propulsion, what safeguards would be necessary? A single accident with such material would not be a local chemical spill. It would be a persistent, high-intensity radioactive event that could render a planetoid or a sector of space uninhabitable for centuries. The containment protocols, the security measures to prevent misuse, the long-term disposal of the waste products from such engines, these are problems that make our current nuclear dilemmas look simple. We would be bottling the aftermath of a star's collision, and we must ask if we are wise enough to unscrew the cap. This knowledge also holds up a mirror, reflecting a startling truth about our own origins. Our bodies, our technology, our very world are built from the debris of unimaginable violence. The gold in a microchip, the uranium in a reactor, the iodine in your body, all were born in a cataclysm that briefly outshone galaxies. This fact challenges our narratives of peaceful creation. We are not the children of a serene, clockwork universe. We are the offspring of chaos and destruction, the beneficiaries of cosmic catastrophe. Does this change how we see ourselves? It suggests that violence and creation are not opposites in the grand scheme, but intertwined forces. The same process that could sterilize a region of space also seeds it with the potential for rocky planets and complex chemistry. This duality is written into our atomic makeup. It forces a humbling perspective. Our existence is not a default state of the universe. It is a fragile, unlikely gift assembled from the ashes of stellar tragedies. So where does this leave humanity's place in such a universe? We are not separate observers. We are participants in an ongoing story of transformation. The elements in our hands today were forged in a past explosion, and our actions now determine what will be built with them in the future. This connects us across time to events billions of years old and to possibilities billions of years hence. Our responsibility, then, is to wield our growing knowledge with a consciousness of that immense timeline. It means looking at that faint crimson glow in the data and seeing not just a power source or a hazard, but a chapter in a story of which we are now the authors. The universe is both artist and destroyer. As we learn to touch its tools, we must decide what kind of creators we will become. The ethical weight of cosmic creation finds its echo in our stories. Long before scientists confirmed the violent origins of gold, storytellers were dreaming of stellar cataclysms and their fallout. Today, the cutting-edge science of macronovae is actively reshaping those narratives, turning a once obscure astrophysical event into a versatile plot device across films, books, and games. In many of these tales, the merger itself is the ultimate doomsday weapon. A common trope involves a rogue faction or ancient alien technology triggering an artificial neutron star collision, aiming its deadly gamma-ray jet at an unsuspecting planet. While the science of focusing such an event is wildly exaggerated, the core threat is grounded. These stories correctly grasp the sheer scale of the energy involved, translating the abstract power of a merger into a visceral galactic-scale stakes. They get the destructive potential chillingly right, even if the control mechanism remains firmly in the realm of fantasy. Beyond pure destruction, the radioactive products of these events fuel countless adventures. In epic space operas, you might find starship captains hunting for kilonova remnants, clouds of debris rich with unstable transuranic elements that can power faster than light drives or charge planet-killing superweapons. The concept of harvesting exotic isotopes for propulsion, as we discussed, is a genuine theoretical idea, though the process is far more gradual and technically monstrous than a simple mining run. These stories brilliantly capture the allure of such materials, their unimaginable energy density, their rarity, their connection to cosmic violence. They turn the abstract concept of the rapid neutron capture process into a tangible treasure, a physical MacGuffin that crews will risk everything to obtain. The science inspires the treasure map, and the fiction makes that map feel real and worth following. Perhaps the most poignant fictional use transforms the radioactive glow into a guide. In some narratives, the persistent afterglow of a long-past merger becomes a literal beacon, a fixed point in a confusing nebula or a waypoint on an ancient hyperspace route. This idea is poetically accurate. As we've seen, that glow is a chemical fingerprint, a unique signature that could, in principle, be catalogued and recognized. A future navigation computer might indeed use the spectral signature of a particular macronova's remnant to triangulate position, much like ancient sailors used stars. The fiction takes this a step further, often imbuing these beacons with mystery or a message from a lost civilization, blending the science of light with the human need for meaning. It gets the what right. The glow is a persistent, identifiable signal, while creatively exploring the so what in deeply human terms. So where do these stories diverge from reality? The primary exaggeration is time. Hollywood compresses billion-year processes into hours. A neutron star merger is not an instant button press event one can trigger on a Tuesday. It's the final moment of a gravitational dance that took hundreds of millions of years to spiral inward. The aftermath is also slowed down. While the glow lasts for weeks, the formation of minimal, solid nuggets of precious metals within the expanding cloud is a process that would take ages, as atoms slowly gather through forces far weaker than gravity in the near-perfect vacuum of space. Furthermore, the sheer intensity of the radiation in a fresh debris cloud is often underplayed. A ship flying into such a region wouldn't just find shiny rocks, it would be sterilized instantly by gamma rays, a detail many adventures conveniently overlook for the sake of the plot. This vibrant back and forth between science and fiction is not a flaw, it's the engine of inspiration. Accurate science provides a foundation of plausibility that makes the incredible stories feel more immersive and thrilling. The fictional extrapolations, in turn, stretch our imaginations, posing questions that future scientists might one day ponder seriously. Could we ever calibrate a gravitational wave emitter? What societal structures would evolve around the control of such a power source? A teenager watching a film about a kilonova-powered starship today might be the physicist who studies nuclear equation of state tomorrow, or the engineer who designs advanced radiation shielding. The stories plant the seed of wonder, and the rigorous science cultivates it into understanding. They are not competing narratives, but complementary chapters in the same epic humanity's attempt to comprehend and eventually converse with the brilliant and violent heart of the cosmos. The journey from a silent cosmic collision to a soft crimson light is a story of transformation written in atomic fire. It begins with the violent merger of two dead stars, a cataclysm that shakes the fabric of space. From that chaos emerges a sustained, radioactive glow, the universe's own alchemist patiently forging gold and uranium from a neutron storm. This same light becomes a cartographer, mapping the chemical evolution of galaxies and highlighting the dangerous, radioactive frontiers between stars. And it whispers to our engineers, hinting at propulsion systems powered by the decay of atoms born in stellar violence. To study this single phenomenon is to bridge vast disciplines. It connects the fundamental physics of matter under impossible pressure to the blueprints for starships we cannot yet build. It ties the cold equations of radioactive half-lives to the warm, philosophical realization that we are the universe's way of understanding its own beautiful, destructive creativity. This is more than astronomy, it is a holistic view of our place in a dynamic cosmos. So the next time you look up at the night sky, remember this: the darkness is not empty. It is filled with the invisible, fading echoes of ancient explosions, each a brilliant chapter in the story of how everything, including us, came to be. Stay curious about the tools, the telescopes, and the technologies that will one day make those echoes visible to all. The universe has been leaving these glowing messages for billions of years. We are just beginning to learn how to read them.